I'm going to quickly go over your test 3 so that you can use it as a study tool in preparing for the final, which is next week. So the first question, which alcohol will most easily undergo acid catalyzed dehydration when treated with concentrated H2SO4? So that's H2SO4 is essentially just, you can treat it as H plus and H2O. Because it's acid, and when you add acid to water that's more acidic than water, it will become H3O plus and HSO4 minus. And if you're not sure which one of these would be favored, you can look up the pKa of each, which is something that we've talked about before. I think the pKa was on top, but for some reason it's not on there now. But it should be. Let me look. Oh well, okay. So I know the pK of this is more, or it's less than negative 1.7. It's more acidic than that. And so I know that when you add it to water and hydronium is negative 1.7, it's going to favor the weaker acid side, and this is the weaker acid side. And you typically have to dissolve H2SO4 in water. So essentially the first thing that will happen is, for all of these, the alcohol will protonate and it will become water. And that water is then a good leaving group, so that then the leaving group can leave. And so you'd get an initial carbocation that looks like this, or this, or this. And so then you have to think which one of these is the most stable initially before it undergoes rearrangement, and that is A, because that one would be the one that goes most quickly, or most easily, is because it's the most stable carbocation, so it'll form the fastest. So A is the right answer here. The next one, which structure represents Z1-bromo-2-methyl-hex-2-ene? So for all of these, first I'm going to look for hexene. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So all these are hexene. The next thing I'm going to look for is the alkene on the second carbon. So in this one it is. In this one it's not. The alkene is on carbon 1. Sorry if you can hear my robot vacuum in the background. This one, it's on, well, I did the numbers backwards, so 1, 2, 3. So it is here on 2, and then this one, it's on 1. So that narrows my answer choice down to 1 or 3. So then the next thing I'm going to look is, do they all have bromo on carbon 1? And they both do. So now is it Z? And Z means that the largest priority are on the same side, or the highest priority is on the same side. So over here we have a CH3 and a CH2 BR. So the CH is, the C is the same, so the H is, and the BR is what we compare. So this is the higher priority. And then down here we have a hydrogen, so this is the lower priority. So that's not right. So then it must be answer choice 3, but I'm just going to double check. We have the CH2 higher priority over here and the BR higher priority over here. So the answer is C. And I just realized that that one's wrong. This is the right answer, so I'll need to make that correction when grading. So if you got that one wrong and you weren't sure why, it's because it was wrong on the key. Sorry about that. Okay, when looking at the reaction below, what would happen to the rate of reaction if you could double the concentration of the nucleophile? So before we can talk about the rate of the reaction, we have to decide which reaction this is. So this is CH3O minus with Na plus. This is negatively charged, so this is a strong nucleophile. So this is either going to be SN2 or E2. What's nice is you actually don't have to figure out if it's SN2 or E2 because the rate of those is the same. It's K times the nucleophile and the substrate. So if we doubled the rate, if you doubled the concentration of the nucleophile, it would double the rate. If we multiplied that times 2, we'd have to multiply that times 2, so the answer is it would double the rate. The rate equation for the nucleophilic substitution of a tertiary alkyl chloride with CH3OH. So we know this is a substitution reaction. So we need to figure out, is it SN1 or SN2? So SN1 has a weak nucleophile usually. And SN2 is a strong nucleophile. So looking at this, I think we have a weak nucleophile, so it's probably SN1, but you need to be able to make a carbocation, so I'm going to also look at the electrophile reaction of a tertiary alkyl chloride with CH3OH. So tertiary alkyl chloride would be something like this, so that would be able to form a good leaving group, so this would be SN1. So the rate equation is, the rate is equal to K times the electrophile. And so that would be just this one. But that did make me realize on this one above, I didn't double check. You can't have a tertiary substrate on an SN2. So just making sure this one was a secondary substrate, and it is secondary or primary. So the nucleophile would be able to come in and attack there and kick that out. Okay. What product would you expect to obtain from the following SN1 reaction? Okay, so if this is SN1, it already tells you, so now you just need to know the mechanism. So the leaving group leaves, and we get a carbocation over here. This side is unchanged. So now the nucleophile can attack, and it can attack from either side. So we'll get a mixture of this being OCH3 on top and the hydrogen on the bottom, and then the side not changing, and then the opposite plus the it's not an enantiomer. Well, is it? Yeah, because that's the only, is that the only chiral center? I guess I'll just say plus the opposite. So you'd also get OCH3 and, oh wait, sorry, I put that in the wrong place. OCH3 on the bottom and H on the top. So you can attack from either side on that carbocation. So when I'm looking at my answer choices, these have the one on the left side that isn't affected. This one has the one on the left side changed and not the one on the right side. So that doesn't make sense. So then I look at this side over here, and it looks like we have one of each. So I think it'd be an equimolar mix of 1 and 2. All right, by analyzing the starting material of the product, the following reaction is possibly an example of what type of mechanism. Be sure to consider the overall reaction, stereochemistry, and the regiochemistry. Okay, so the first thing I'm looking at is we started with a chlorine and we ended up with an iodine. So this is a substitution. And then to really tell the difference between substitution, SN1 gives you a mixture and SN2 gives you one product, just the inverse. So this looks like a mixture to me, and in fact, if I flipped this over, it would be this. So I know that because we got both of these, it must be an SN1 reaction. Okay, which of the following represents Markovnikov addition of water across a double bond with anti-stereochemistry? So I'm looking for adding H on one side, OH on the other. Markovnikov means that the OH is the nucleophile, goes on the more substituted side. And the anti-stereochemistry means the H and the OH are opposite, like wedge dash. So what I'm looking for, I'm not even going to look at my answer choices. I just know that we're going to get our OH over here. Going to get rid of that. And then we're going to get an H that's the opposite. But there is also an H already that's a dash, so that doesn't really matter, I guess. But our CH3 will be here and our OH will be there. Okay, so that's what I'm looking for. So first I'm going to make sure to eliminate any that don't add an OH. So this one adds 2 OHs, so that's not right. This one does add an OH and an H, so that's a good place to start. This also adds an OH and an H. And this also adds an OH and an H. But if it's Markovnikov, the OH ends up on the more substituted side. So if we started with this CH3 over here, then that's where the OH needs to be. This one looks like the OH is with the less substituted side, so that's not right. And same thing here, the OH is with the less substituted side, so this is our only possible answer, so answer C. Okay, rank the following from lowest to highest heat of hydrogenation. So we're going from the most stable to the least stable. So most stable is most substituted. Least stable is least substituted. So I'm just first going to say this one, there's, instead of any hydrogens at all, actually I guess I'll start with this one. So see how there's 2 hydrogens here, 2 hydrogens here, only 1 hydrogen here, and no hydrogens here. So the less hydrogens is essentially the more substituted. We're substituting hydrogens out for other things. Sorry, my robot vacuum's in the other room going crazy. Okay, we call her Rita. Rita the robot vacuum is wild. And all right, so this one is, we would say, tetrasubstituted. So this is the most substituted, so this is the most stable. And then these two are the least substituted. And honestly, it's hard for me to ever remember which one of these is more stable. But it could be either of these two. And right now I'm like, oh, I don't remember off the top of my head which one of these is more stable. But I do at least know that this tetrasubstituted is the most stable. Hang on, I think it's getting a cord. Okay, I'm back. Usually, I'm thinking like, okay, this tetrasubstituted is the most stable. This is the next most stable. And I honestly can't remember off the top of my head, but I know these two, they're not equal, but they're close. So looking at this, I'm thinking, all right, well, first I'm just going to eliminate any that don't start with 1 as the most stable. So this one can't be right, this one can't be right, this one can't be right. So I've narrowed it down to this one and this one. And I know that 2 is the next most stable, so this one can't be right. So this must be the right answer. So I guess that having 2 hydrogens on the same side is more stable than having 2 hydrogens on opposite carbons. All right, so next question. Treating 1-methylcyclohexene with HCl would yield primarily which of these? So here is cyclohexene. It has a methyl on it, and we're treating it with HCl. So HCl. We'll have a positive charge here and a Cl minus here. So we have the CH3 and the Cl would attack right there. So this is what we would get. So to me, this looks like answer choice C. This one is wrong because the carbocation would have been on the less substituted carbon, and that's not what happens when we add that H initially. This one is wrong because it still has the alkene. This one doesn't add the chlorine where the alkene is, and same thing here. This one didn't add the chlorine where the alkene was. So answer choice C. Okay. The regiochemistry and stereochemistry and hydroboration oxidation of the alkene is best described as hydroboration oxidation is adding water across a double bond. It typically goes by anti-Markovnikov. And you can think of the double bond that sort of makes that box if you had a CH3 perhaps over here. It makes a box sort of like this. And so the boron goes to the less substituted side, and that's eventually where the alcohol ends up. So I'm looking for anti-Markovnikov, but because it makes a box, it sort of does a syn stereochemistry. So Markovnikov, that's wrong. Markovnikov, that's wrong. Markovnikov, that's wrong. So if you didn't know that it does syn addition, you could at least get it down to a 50-50 shot. And then here is our anti-Markovnikov. Next question is predict the product of the following reaction. So I see a nucleophile, I see a leaving group. I see a nucleophile, and I see heat. So the leaving group, nucleophile and heat, makes me think this could be SN2, E2, E1, or SN1. The nucleophile is weak, so that makes me think it's going to be an E1 or an SN1. And between, then I'm going to double check and make sure the leaving group can leave, and that's true. The leaving group leaves, and there'd be a carbocation right there. It's secondary, not a primary, so that works. So it could be one of those. And then heat makes me think E1 over SN1. So I think this is going to be an elimination reaction. So the leaving group would leave, and you're going to get this secondary carbocation, which will rearrange to right here. And then you will get an elimination. So we could take a hydrogen from one of many spots here, but we're going to try to get the most substituted one. So I'm going to draw all the potential substitutions that could take place. If I took from the hydrogen right here, we would get an alkene form here. If I took from the hydrogen, so I guess I'll do this right here, and then I'll do this one. We would get, this one would still be the same, this, and then if I took from the green one, we would get this. So I'm looking to see which one of these is the most stable. So this is tetrasubstituted. This has, or actually I'm just looking at all the options. This is tetrasubstituted, this is tri-substituted, and so is this tri-substituted. So then the next question we ask is it gonna favor the more substituted or less substituted? Another way of asking that is this Hoffman or Zaitsev? And because this is a narrow nucleophile, the more substituted, more stable Zaitsev product is going to be favored, and the more substituted, most stable is this one right here. So that would be answer choice C. Oh, it looks like I have the wrong answer on this one. So also if you got that one wrong, I will double check that as well. Just making sure that, yeah, rearrangement and then the hydrogen here. Sorry, there goes my robot vacuum again. Yeah, I think that I put the wrong answer on that, so I'll double check that. All right, what is the rate determining step of an SN2 reaction? So SN2 reaction is actually just one step. So the one step is the rate determining. So the leaving group leaving and the nucleophile attacking. If we were talking about an SN1, the leaving group leaving and carbocation forming, this is the same step. So that was one clue that those probably weren't right. And then protonation of an alcohol, that would just be acid base. That actually is not an SN2 reaction. Which of the given structures would result from the following reaction? So O3 with DMS, that's just going to cleave that double bond and add an oxygen on either side. So let me make sure I don't have, sometimes I worry about getting too many carbons, so sometimes I'll just draw it like this, and then draw the other rest of it, even though it looks weird. 1, 2, 3, 4, 5, 6. And then over here is an aldehyde, and that doesn't change. And so we need a 6-membered carbon. 1, 2, 3 carbon chain. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. This is 6, but the ends are, the ketones aren't in the right place. And then this doesn't cleave at all. So this is answer choice B. Okay, which of the structures would result from the following reaction? Cold dilute KMNO4 adds alcohol across a double bond. And so that would be answer choice D as well. Which of the reagents below would convert cyclopentene into cyclopentane? That is a hydrogenation reaction, and we actually learned that in a previous chapter, so it's just kind of coming back. Okay, The following reaction will not proceed as written by an E2. Explain why not and what you would change to accomplish the reaction. So this OH is, I guess when I think of E2 reaction, we need a strong nucleophile, a good leaving group, and we need a reason for it to favor E2 over SN2. So when I'm looking at this, we have a strong nucleophile, we have heat, which favors E2 over SN2, but we don't have a good leaving group. So my answer to this would be, it would not proceed because we do not have a strong leaving group. So instead of OH, I would put a different leaving group. And you might be thinking that you could just add H plus to protonate it to make it a good leaving group. But actually, it would not protonate that. If you add H plus, it would just make it HOH. So that wouldn't be an option. You need to put a different leaving group. So just saying that would be enough. Not saying that you protonated it. You only get partial credit for that. Okay, the following reaction would undergo a bimolecular substitution, SN2, even though it's a weak nucleophile. Explain why. So when I'm thinking about SN1, SN2, E1, E2, I'm thinking about SN2 needs a weak nucleophile, needs a strong nucleophile. It needs a primary or secondary leaving group, and it needs to be a good leaving group, and not too bulky nucleophile as well. So when I'm looking at this and it has a weak nucleophile, I'm like, well, why wouldn't that go SN1? SN1 needs a good leaving group, needs to be secondary, tertiary, a weak nucleophile, and it doesn't matter if it's bulky or not. So when I'm looking at this, I'm like, this has a weak nucleophile, and it has a good leaving group, but the leaving group is on a primary. So if it left, it would make a primary carbocation, which would not form. So it would be easier, even though it's unlikely, for this to come in and attack and kick out rather than waiting for the leaving group to leave, because that's just not going to happen. So my explanation, I'm not going to write it all out here, but because the leaving group would not form a stable carbocation, SN2 would ultimately be favored. It's not going to be a good SN2 reaction, but it will be an SN2 reaction. Okay, and then the last question, which of the following carbocations would be likely to undergo rearrangement? So if I'm looking at carbocations that could undergo rearrangement, they need to be next to a more substituted, but it can only be hydrogen or methyl can shift over. So that's what I'm looking for. Next to a more substituted carbon, and hydrogen or methyl shift over. So this one is next to a more substituted carbon. This one is not. It's already on a substituted carbon. This one is already on a substituted carbon. The one next to it is not more substituted. This is next to a more substituted carbon. This is next to a more substituted carbon. And this is next to a more substituted carbon. Then, okay, we need to only look for hydrogen shift or methyl shift. So here we have a methyl that could shift over and leave that side. So that would work. So I'm going to say definitely 1. This one, we only have ethyls, and ethyls can't shift over, only hydrogens or methyls, so that won't work. This one, we have there is a cardinal in my garden. It's probably going to eat my sunflower seeds. This one, we have a methyl or a hydrogen. Hydrogen's easier to shift over, so the hydrogen would shift over, and it would actually end up looking like this one right above it. So that one would work. And then this one, it is right next to, it has 2 hydrogens here that one of these could shift over. So that one would work as well. So 1, 5, and 6 are the ones that would work. Okay, I hope that was helpful to you. Good luck studying for your final. I've really enjoyed getting to know y'all this semester, and let me know if I can help with anything.